Having talked previously about pressure, now we'll continue our conversation in flow. So what is flow? Well, basically when we're trying to measure flow, we're trying to work out how much of something has moved from some spot to a different spot. So we're looking at the quantity of material that's moved from point A to point B, for example. And typically we use this talking about how much of a liquid or how much of a gas has moved from point A to point B. Now, this is used for many different applications, and we'll talk about some of those applications, but one of the ones that we probably see all the time, or as we walk past outside of our house each day, is the one above. This is how water authorities know how much water we've used, and we've got a similar one for our natural gas. Each time we turn on the tap, the little wheels in here will turn, recording that we've used extra litres of water or extra natural gas for maybe our heating or our water heating and things like that. Now, we can measure this flow in terms of mass or volume over a period of time. So flow's a unit of mass or volume over time. Our flow rate can be affected by a few different things. For example, the size of the pipes or the size of the conduit that our material is going through, or the shape of it as well. We have the actual system or device that we're actually using. We've got how we're actually trying to propel that through the system, the fluid pressure that we're dealing with, and also the viscosity of our liquid that we're trying to move. For example, it's a bit trickier to move honey compared to water, which is a whole lot less viscous than honey. So when we're talking about flow, we can talk about a steady state flow or a dynamic flow. Sometimes our flow, for example, if we turn on the tap, we have water coming out, but sometimes that flow will change, particularly if we've got one of those trigger guns and we keep on cutting off the flow and releasing the flow and spraying water out. We've got flow that is quite variable and changing there. We might have electronic actuators in there cutting out the flow or attenuating that flow and changing it multiple times a second, potentially over time. One place that you might see this flow is in traditional inkjet printers. And here you're printing tiny little dots, and we're looking at the flow of that ink coming out from each of our cartridges. We're talking about tiny, tiny microliters worth of ink, but they're being deposited very rapidly. And on some spots they're deposited, on other spots they're not deposited, and we can use that to mix our various colors together. Now, flow can be laminar, which means it's nice and smooth, or it can be turbulent, which means we have swirls occurring within our flow as it goes through the pipe. Now, we've got a few different ways of measuring flow. Most of the ways to measure flow, although there are some direct ways of measuring flow, are indirect. So we're measuring change in pressure, for example, or we're measuring the velocity of the liquid through the pipe. And we use the pipe dimensions to infer flow from that. And we use something called a flow sensor, which is often called a flow meter. Now, before we get on to all the liquid and gas flow, which is primarily what we use these sensors for and primarily what we'll be talking about, we should mention that we can measure flow in a solid sense. When we're talking about flow in a solid sense, think, for example, of a conveyor belt. And that conveyor belt, well, we might have a whole lot of material being deposited on there. That might be rock that we're moving across, or it might be grain, for example, that we're moving across. And we might have a sensor underneath there that measures, for example, the weight of the material, a little load cell which measures the weight of the material as it goes across. And depending on how uniform the material is deposited over our conveyor belt, well, that weight may increase or decrease. We may have a change in flow. And if we integrate that over time, we can work out what our flow is. Because remember, we're looking at, in this case, a mass over time. There's other ways you can see above that we can measure flow as well, for example, for these solid materials. We've got, for example, our impact plate, where we're measuring deflection of some maybe grain or wheat that's pushing against that plate. And as we push it further, we can actually measure how much flow based on the mass that's hitting that plate. Likewise, with the centrifugal one, we can measure the force that's being applied to our force sensor there based on how much mass of grain or whatever it is that we're trying to measure. Could be rocks, for example. With our Coriolis one, we've got a spinning disc there, and all of the material as it passes through moves to the edge. And the more mass that's on that disc, well, the harder it's going to be to actually turn that disc and keep it up at speed. So we can measure the torque that is being placed on that particular disc due to what's actually falling on top of it. We can also measure capacitance and the change in capacitance from, example, an empty tube to a full tube, or we can use microwave and measure the Doppler effect as solid particles move through a particular tube or a carriageway. So our units of flow will actually depend on what we're measuring. So for example, if we're measuring solids, we might be looking at grams or kilograms per hour or tons per hour or something like that. If we're looking at liquids, we could be looking at a volume or a weight per unit time, seconds or hours or whatever it may be. When we're looking at gases, we're typically looking at volume over time. And we typically specify a temperature and pressure that we're dealing with during those things. And finally, when we're looking at, for example, steam, we might do this as a comparison of how much water was used to actually produce that steam to begin with. And so we might use our weight measurement, once again, weight over time. Now we've looked at pressure previously, and now we're looking at flow. And it's helpful to think about the relationship between these two. Remember, pressure is a force per unit area that is exerted by that force over a particular unit area. And we can measure that, for example, using our SI unit as newtons per square meter, force, which is a force per unit area. Now we're looking at flow, and we're looking how much of a fluid, typically a fluid, but it could be a solid, has moved through a system in a given amount of time. And so we're looking at a volume or mass over time. Now these are related by Poiseuille's law. We've got it there where our change in pressure, where we've got mu, which is our viscosity of the fluid that we're trying to transport. We've got L, which is the pipe length that we're trying to transport it over. We've got Q, which is our volumetric flow rate. And we've got R, which is our pipe radius. Now, when we're thinking about flow and trying to measure flow in a system, there's lots and lots of different factors that we need to take into account. And taking these different factors into account will help us choose what different flow meter we should choose and how we should actually implement it. One of the major factors is what sort of material are we actually trying to measure? For example, is it a solid, liquid, or gas, which is a really fundamental question. And does it have granules, or is it clear? Can you actually put an ultrasound beam through it, for example? Is it something that's very rough that some of our more mechanical flow meters that would be destroyed by the particular material going through there? Are we needing a measurement based on volume or mass, for example? And this will change particularly when we're moving from liquids to gases, for example. There's lots of conditions around, for example, temperature and pressure and vibration and viscosity of the particular material that we're using. For example, some flow meters will work well when we've got a decent amount of flow, but when we've got very low flows, will perform poorly. Or maybe we've got a very viscous material like our honey or like crude oil or something like that, for example, compared to something that is a whole lot less viscous like water. Now, some materials that we might be trying to transport might be a lot more dangerous to our environment that we're trying to measure. For example, they might be heavily acidic or corrosive. They might have a whole lot of particles in there that eat away at the pipes and cause cavitation, for example. And some materials are electrically conductive and some are not. So they'll have different magnetic properties to them, which may rule out or rule in some different types of flow sensors that we could use. Sometimes we might need non-contact flow measurements. For example, if we're using some food products that we don't want to be contaminated by the actual flow sensors that we're using. Some applications that might not be an issue at all, so we can use these more contact-based methods that don't need to be pristinely cleaned, for example. We've got different things about how the flow sensor needs to put an output, what sort of range that output needs to be over. Like, are we talking a low flow sort of measurement system or a very high flow measurement system, for example? Sometimes the amount of pressure loss in the system is an issue. For example, some of our flow sensors sense flow based on constricting our pipes or our conduit that we're flowing through. In doing so, we might need a high pressure pump to actually supply our liquid or gas to these particular systems. And then we've got things about how the materials are actually carried through the system, whether it be pipe diameters, whether it be conveyor belts for those solid flows, for example. Now, there's lots of different applications for actually measuring flow. Everything from charging us for how much petrol or natural gas or water that we use. Looking at our internal combustion engine and looking at our air fuel mix to make sure we get an optimum air fuel mix. Looking in the medical space, for example, looking at how much flow of oxygen we've got through a medical ventilator, or measurement of our blood pressure, or airflow from our lungs. In mining areas where we might be dredging, where we're looking at how much material are we moving from something, or how much oil are we actually collecting, or how much coal are we collecting for more of a solid flow application. We can use flow detection for trying to identify if there's a pipe leak or a rupture in a pipe, and we're trying to work out where that rupture may have occurred. Fundamentally though, anytime we're looking at how much material has moved from location A to location B, we have some sort of a flow measurement happening.